Please give a great round of applause to Chahan Yeretzian.
Okay, hi everybody. So be relaxed because you will get now a little bit hard stuff to digest because extraction is a really complex subject. So I will not do it too simple, but I will try to keep always such that you can follow. And so first one slide about the Coffee Excellence Center. It's a group, of course, and we have different eras. And last week, some might have seen Samo. Samo was here to talk about one particular aspect of coffee research, which is the degassing, the CO2, and how it is released. Some people might know Marco. He wrote recently a coffee booklet on water, but he knows much more. Sebastian is more on green coffee. And then we have Anya, who is really focused on aroma generation. And Sabine is doing sustainability and other aspects of our group. So I like to start with extraction. When you look into extraction, there are of course a lot of different parameters that will affect your process. It's not just yield and strength, it's many other things. It's temperature, it's grinding, and the list can go on and on. And that's where actually the problem comes. You know, when you look at that, you don't know really how to attack this issue. And some of these properties are related to the coffee, other to the water, and some other techniques. So if you can extraction, you can do espresso or filter extraction, it's very different. So what happened is, and that happened a long time ago, people try to simplify things. You have to find out which are the key parameters in order to bring order into discussion about extraction. So what was done initially, and that was in the 57, 59, there was the Dr. Lockhart who came up with the Brewing Chart, brew control chart, or how you want to call it. And this is something that we are still using today. What he did is he said that there are 3 parameters that are of particularly high importance. One is the yield, the second is the strength, and the third is the brewing ratio. And what he did is he said that there are one input parameter, which is essentially the ratio. This is an input parameter. You decide yourself how you want to do it. And there are 2 output parameters you can measure in a simple way. We have instrument, and with that you can describe the extraction. This is a very high oversimplification of the process, but at the same time, it brings us a way to discuss extraction. So we have to find a compromise. I'd like to show you a little bit throughout this talk, a little bit what are shortcomings, what are the strengths, and perhaps how we could go on. And in a way, this brewing chart, I'd like to compare to the people who work on roasting. You know, last week, the Roasters Guild was here. And if you would think about the roasting, thinking in the same language, having one input parameter, which would be, say, the blend and the variety, and one output parameter, which is the roast degree, that would be really a very simplistic way of talking about roasting. They have, of course, introduced in the meantime the roast profile and discuss it in all details. When you come to brewing, there is nothing like that. We only discuss about one input parameter, 2 output parameters, and we believe that we have a good understanding of the brewing process. But we don't look at the dynamics. And the roasting people, they have developed since quite a while now the dynamic aspect. How does it evolve during the roasting process? And also they have a much more molecular understanding. They try to understand what's happening during different phases. So I think in a way they are ahead of what's happening in the brewing. Why that's the case, I can't really know, but I think what we should be doing in the brewing era is to go also into a different way of looking at the brewing, include a more molecular understanding as well as a dynamic understanding of the brewing process, a little bit like the people in roasting have done it and successfully. Now, I'd like to show you a similar thing that we did just recently. In the water, we had the same issue. Water, if you want to describe water, there are so many parameters that are relevant. You can talk about all this total hardness, carbonate hardness. So the first issue is to define these different terms properly. And second is to define which are important. And that's what we have been doing in this SCA water chart, where we define 2 parameters, alkalinity and total hardness, as the driver, for water description, and defined also there something like the ideal area, this core zone, just as in the brewing. So simplification is necessary, of course, in order to be able to talk about things. At the same time, they bring also a narrowing of the horizon if you stick too much to this kind of description. So I'm coming back now to the brewing chart that we are using, or you are using all the time. It has actually two characteristics. First of all, it is a macroscopic picture. You have the yield as a number that includes everything in one number. And the other one, it is a static picture. In some sense, it describes the final cup. It doesn't really describe the path, how you get to the cup. So these are the two characteristics of the brewing chart. And when you are somewhere in a place, you are describing the final situation of your cup, but you don't know really how you got there. Now, the future, probably, of a better understanding of the brewing process is to include a more microscopic molecular understanding, because caffeine, aroma, melanoidin are all behaving very differently, and it's actually interesting to look into a little bit into these differences in order to understand how perhaps the future form of a brewing chart should look like. And the other thing is to look into time-resolved way. How is actually the extraction process running from the first drop to the final cup? And how are differences between a filter coffee and espresso? And then perhaps through that, get a different way of looking at the roasting. So I'd like to develop today these two aspects, and at the same time, always look at the brewing chart. So what I'd like to do is I will talk a little bit about different extraction method, espresso extraction from a single serve as well as professional machine. Then we also work on the fully automatic machine, coming back to espresso machine, and then filter extraction, and then revisiting a little bit the brewing chart throughout of that. Really the way we're working is the following. In the first phase, and that we're fully still in that phase, is we are doing exploratory work on extraction, very broad research on understanding extraction in different systems in order to understand better what's happening. And then in the second phase, we try to reflect that what we have learned in the framework of the brewing chart. Can we project this kind of information we're getting on the brewing chart? Can the brewing chart be extended in order to include this dynamic and molecular information? And third, and this I will not discuss today, but perhaps that's like where we're going, is there a next generation brewing chart that could be still simple, useful, understandable, but perhaps it will be able to describe a little bit more about the brewing concept. A study that we did, it's published, is we look, for example, at 9 different extraction ways, Dallacort, espresso, lungo, capsule, Bialetti, Bodum, Carlsbader, Canyon filter coffee. And we looked at different analytical measurements, and we looked also, we analyzed in this case, we did 3 different type of coffees. One is how much is in a sip, how much is in the full cup, and what is the extraction when we look at the coffee or the brew ratio. So this work, I'm not going to discuss here because it's a published work. We develop identity cards, but you already realize that you have a huge diversity just from the preparation method. And the brewing chart is somehow, for each one, you would have to develop another one, which is being done, of course. So first of all, the range of extraction techniques, which I will not discuss today, I will go into a professional machine. I will discuss the fully automatic machine and then the filter coffee today. So first of all, I'd like to start with extraction, and I would like to develop particularly now the molecular picture as well as a dynamic picture of extraction on specific cases. So looking in one case, in another case, and the individual case, and perhaps at the end we can bring that together into something that is meaningful. So there are, of course, parameters on the coffee side, parameters on the water side that we have to consider. And the first experiment we did is with single-serve capsules. Of course, it's kind of weird to say that, but the reason why we do that, in the first place, we always go to a system where the extraction is of no issue. because we have first to master the analytics, the measurements, to get proper measurements. So we start with a simple extraction method where it's like a push button, and then once we have that, we can go to a fully automatic or to a, of course, then to a professional machine, which is much more complex because then you have to deal with both issues. And to do high reproducible extraction on a professional machine is much more challenging. But this is actually the beginning of good science. You have to have reproducible extraction. So that's why we started with single-serve systems. I'd like to show you the first experiment we did. Here is a single-serve capsule system. The capsule goes in here, and the flow goes down here into this beaker. The beaker is actually cooled, ice-cooled. We don't see it here because we don't want that flavor coming back is being measured here, because here is a very small sensor that measures the full aroma of the coffee. So what you have is you have the coffee flowing down like that out of the exit here, and at right angle we are measuring with a sensor the full aroma at a high time resolution. I'm not going to describe how that works. It's a very sophisticated machine, and not many people can have that. So just the instrument costs $500,000. So it's not something you can reproduce. It's more to understand the process. But here, with a very thin capillary, we are smelling on the water that is flowing down, and we are analyzing the flavor at the resolution of 1 second. Here you see it. This is the way and then we go into the instrument and we get the flavor profile. And we did it for a large number of different capsules. This work is also published and can be read. So here are now some of these compounds. These are 4 compounds which are given name here, that are known flavor compounds of coffee. And you see that some compounds, when you start the extraction, when the flow starts, you get a high intensity initially, and then after 10, 15 seconds, you hardly have any intensity anymore when you sniff on the water, on the extract, which means it disappears. Whereas other compounds come much later and stay much longer until you stop the extraction. So first of all, you see a very differential extraction of flavor compounds over the extraction process, which means, of course, as we know, we have a change in flavor profile of the coffee. So we're looking at the molecular level, individual flavor compounds, how they are being extracted when you extract it from a single-serve espresso system. This is a molecular picture, and here you have the integral. If you integrate the amount of aroma, and here you are at 100, we work often like that. We say the total amount of this compound in the final cup is 100. How does it come into the cup over the extraction process? So you see that some compounds, already after 10 seconds, have 70% of the aroma is already in the cup. Whereas in other compounds, you have only like 15 to 20% after 10 seconds. So you have basically what that shows is that the flavor profile is evolving and changing during the extraction. And we can look at that now in a very detailed manner in order to understand how this evolves. Now you can look at you have 92 compounds, and you can look them in different ways. Here is looking from the top. Wherever you have the red point, the compound reaches its maximum in the extraction and then goes down. And you see that most compounds reach basically their maximum in the extraction at around 5 to 7 seconds in the extraction process. And then they already go down. Basically what you're doing is you're already diluting after 7 seconds. Whereas a few compounds come much later, and they are responsible for the taste of a longer extract. And so you can get this data. And you can also these are 6 different capsules. When you sniff on it and you do statistical analysis, you can differentiate it within 1 second which coffee you are sniffing on, because the profile of each coffee is different, and they have each different ways of extracting the flavor. And statistically, you have here 10 repetitions of each one, and they are each clearly assigned. So this kind of information not only sees the details, it also can clearly differentiate a flavor profile within a second, saying this is this coffee, this is the other coffee, just by looking at the flavor profile. Now, we did that for the capsule system because it's easier to understand what we're doing. Now we went on to a semi-automatic now, to a professional machine, and try to replicate the same thing. And we wanted here also to address the issue of extraction parameter. How does temperature, pressure, and water affect now these different extractions? Are they affecting them, and how are they affecting the extraction process? Because these are three important parameters. Now, for the water, we didn't see any effect, just because we have, of course, we have significant standard deviations in the measurements. It's not easy. If you measure with a semi-automatic machine, to be reproducible is quite difficult. Even the flow moves a little bit like that, which is quite difficult for our experiment. So, but overall, we got some decent results. This is also published in 2016 in a publication. So this was our first experiment. What we did is we call that the central point. This is like the regular extraction conditions. And first we looked at how is it happening, what's happening here. And then we moved the temperature and the pressure and also the water. I'm not showing here because the water didn't show any effect. And we extracted this on this machine. And we were sniffing here, going down on the flow in order to see the flavor compounds. Now we're looking, and here are different flavor compounds. What we could find are different families, some compound. Here you have, before the flow comes, we already sniff something, because when you wet the coffee already starts, the aroma already is coming from the bottom side out without any flow. Basically, you have already some emanation of aroma on the sensor, and the flow starts here, and then you see that this compound, this is a family of compound, and we found 7 compounds which behave exactly like that. They come, have a maximum at around 12 seconds, and then go down. And then we have another family of 6 compounds which have a slower extraction. This compound has, you smell it even earlier, before the flow comes, and then slower and slower. So we have different family of compounds, and you can understand the differences by the physical property of these aroma compounds. It has to do mainly with the polarity, with the water solubility, and you can see why some compounds comes much earlier in the extract and some comes later. And here again, you see, of course, in this type of extraction, the intensities are much higher still here at the end of the extraction. This is a 25 milliliter extraction. And you see again here these significant differences in different flavor compounds, how they are extracted. And depending on how long you extract, you will have a different flavor profile. This is the polarity. Now the other effect is pressure and temperature. Now, does pressure affect the extraction? Some compounds are affected, like here. This one has also an effect, but in fact, this compound, which is not actually a flavor compound, but it's an interesting behavior, it comes earlier. Some of the compounds here at 11 bar comes faster, but then at longer time, it doesn't show any effect of the pressure, 0 effect. And there are actually many compounds which are not at all affected by the extraction pressure. You can change it from, in that range, from 7 to 11, it comes the same way. Other compounds have significant differences, and here you see that what we observe in general is that 7 and 9 show small differences. If you go to 11, you start to see a difference. So it's not like a homogeneous change. So some 7 and 9 have very similar extraction behavior, but then the 11 is a little bit more, and you don't see differences here. Here is basically the total amount in the cup, and this is significantly more than in the other two for the 7 and 9. The 11 will have significantly more at the end. So you see effects with the pressure, and it is dependent on the compound. For the temperature, I believe, I don't know what you would expect, temperature has a bigger effect. And here are again the same 2 compounds. You see here that, again, this compound is not that much affected by the temperature, a little bit, whereas the other one, which has a green flavor, the pyrazine is kind of a green flavor, is strongly affected by temperature, as we would expect. If we go from 82 to 92 to 96 degree, the amount of the aroma that is being extracted is strongly changing. And here again, it's not like everything comes more or less. It depends on the compounds that we're looking at, and it will affect the extraction behavior as a function of the temperature. So we have a much more differentiating perspective on these compounds, and we can look at the flavor properties, but we can see now this phenomena in a a portafilter. Of course, these bars is the standard deviation, so we always have an uncertainty, but in this case, since differences are big, we can clearly differentiate the compounds, and we can say that the temperature has an effect. Overall, temperature has a much bigger effect on the extraction than the pressure. Now, we didn't see any effect on water, so we went back to get a little bit more a handle on the extraction, went to a fully automatic machine. And this is a sharer coffee machine. I don't know if I didn't see here one, but we are close. Workshare is in Switzerland. And so what we did here is, in all the work that I just showed now, we looked into the volatile, which I call aroma, the compounds that are just going out of the coffee into the air, volatile compounds. But when we talk about the brewing chart even doesn't know anything about volatiles. It just only talks about the non-volatiles, about the total solids. So this whole area that I've been talking about is not even in the brewing chart, because it doesn't talk about aroma. Only if you go into the extremes, you have some over-extraction or the bitterness, but this is very little aroma interest. So what we said is we want to go into the same kind of experiments, but we'd like now to go closer to the brewing chart, to look at the compounds that contribute to the yield and to the total dissolved solid. So what we did in this case is we collected samples, fractions along the extraction, and we collected here 8 fractions, and we looked at each individual fraction individually, chemically, to look what are now the compounds that are coming in these fractions that might contribute to the TDS. And here we had a longer cup, which is kind of typical for the fully automatic type of coffee that you use, and we had a brew ratio of 3 and brewing temperature of 90. And then we collected different samples. And here is now first a global picture. First of all, a gravimetric picture of the evolution of the beverage weight as a function of time. And here are 5 repetitions to show a little bit. You have first, of course, a grinding going on in this machine. It's a fully automatic, and then you start the collection of the samples. You have at some point the end, the flow time, the beverage weight, and TDS and yield, which are typical yields as you might expect for espresso. Perhaps for some it's too low, but this is what you can do with a fully automatic machine. And so you end up with such a extraction time, and you see that in this machine, the evolution, at the end of the extraction, it starts to slow down. This has, of course, to do with the pump characteristics and the way, but it is nearly straight line, but not totally. It starts to slow down. And what's also interesting here is in a full automatic machine, at the end what you do is you stop the pump, and there's one more drop coming at the end, and this gives you some additional weight that you see in the gravimetric measurements. It's turning off the pump of your fully automatic machines. So that's why it has this there. Now this is a description of the full cup. It's not a dynamic picture. And now what we wanted is to do also for this now a dynamic picture and looking at how different components are being extracted during the process. And there now we can make the link to the brewing chart, because we're looking at the components that are relevant to the brewing chart. So here is now the first element, which is very at the center of the brewing chart, which is the total dissolved solid. In this case, what we're looking at are the total dissolved salt in each individual fractions. So this one is not the total dissolved salt in the final cup, it is the TDS in the final fraction. And so this is not yet the way we look the brewing chart, because in the brewing chart we integrate, we look always at the sum of everything. But these are essentially what you see in the first fraction. You have a TDS of about 16, 14, 11, 8, goes slowly down, and then in the last fraction you have something like 2.5 total DDS. Now I'm going to convert that into the brewing chart. And if you do that, first I'd like to mention this parameter. That has been, for us, it's quite surprising. We can fit a formula into it, which is very simple, which is a single exponential decay. So basically we can, with this formula, we can predict the evolution of the total dissolved solid by having one parameter, which is this tau. Here it is 10, and the smaller this number, the faster this compound is being extracted. And you can start to compare now between a filter coffee, an espresso extraction, the dynamics of the extraction. So here, whatever that number is, we'll see later, it's a 10, it's extracting at the speed 10, and the smaller, the faster. Now, let's jump to the way we would show it in a brewing chart. Now, in general, what you do is you aim at this point, which is the final cup, and you have here a strength of approximately 7 point something, I said, and extracted a yield of 21. This is the final cup. But if you look how the cup evolves, because we have the first fraction, we can make the first plus the second, plus the third, the fourth, the fifth, we see that the way, the trajectory of this cup looks something like that. And in fact, what is surprising, we'll see later in comparison to, for example, the Nova Simonelli, is that the second fraction has still a significant amount of total solid coming relative to the first. And if we plot that now with the brew ratio, because we know what our brew ratio is in this experiment, it's 3. At the same time, we know what more or less the ideal range is for an extraction in espresso. This is the square that we plot in general as the ideal zone on the brewing chart. So you see that this process starts somewhere here and ends up in this zone, a little bit on the upper right corner, but it is there where it should be. But now we have a dynamic picture of our cup, how it is evolving while extracting. And it gives us a possibility to use the brewing chart and now have a picture that is not just a static endpoint description, but it is a dynamic description of the process, how it gets there. And this is now for a concept that we know, which is the strengths. Now, we can do that for any compounds. We can look at caffeine. Caffeine also, we can measure the caffeine content as a function of time in fraction 1, 2, 3, 4, 5, 6, 7, 8. And we can measure that for many other compounds. For example, here, what you see, for example, this tau is 15, which means it is being extracted slower than the total dissolved solid. So within the total dissolved solid, this is part of total dissolved solid, the chlorogenic acids. But within all the compounds that are being extracted, it is one that is being extracted rather slow compared to the total dissolved solid. These are now chlorogenic acids. We looked at each one. I'm not going to make it too complicated, but these are, in coffee, you have 10% of your total of the weight of a coffee is chlorogenic acids. And then you can look at these compounds, how they are being. And each one, what we have been finding is that they all follow this very simple exponential decay rate. So you can actually follow the way they are extracting from fraction to fraction by using a very simple exponential decay formula and use this number as a reference to compare different compounds to each other to say something about the speed at which they are being extracted. The smaller the number, the slower, the smaller the number, the faster, the bigger the number, the slower. So here you can look at each individual chlorogenic acid or make an average of 3. You can look at the melanoidin. The melanoidin is, I don't know if you know what these are very big compounds. They give the color to our coffee. They're brown components, they are huge molecules. What is surprising is that they are being extracted very fast because again, from the first to the last fraction, you can measure the amount, and you get here a tau factor that is 10, which means it's being extracted quite fast. You would generally say big compounds are being extracted slow, but it doesn't seem to be the fact here. It's actually quite fast. And you see that perhaps when you look at the coffee, the color of your extract. But so you get this kind of information, and then the acidity. We also measure the acidity, and the acidity is, I have to explain, it is the titrable acidity. We measure acidity by titrating the extract with a base, which is a way to determine the total amount of acids in it. The pH is of no value for measuring acidity. You can make a filter coffee or an espresso, you get the same pH, around 5.5. It doesn't tell you anything about perceived acidity, the pH. But the treatable acidity is a way, what it is actually, is you take your coffee and you drop a base in it, some compound, and you measure how the pH changes in your coffee. And it measures the resistance to changing its pH. So if it has a lot of acids in it, it will resist a lot. And the treatable acidity will go up. If it has hardly any acid, it will not resist, and the pH will move up immediately with a few milliliter of putting base in it. So the treatable acidity is a good measure, is the best measure we have to predict the perceived acidity. So that's why we use this technique, and you see here again, acidity is increasing, and of course decreasing. And you see that this number is small, it's the smallest, so which means that the acidity comes very early during extraction because it decreases very fast. It's a small number, that's why it decreases very fast, whereas other compounds come much slower out. So acidity is the compound, is the quality that is decreasing the fastest, which is probably the most prominent in the very early phases of the extraction. That's what this small number tells us. And then we can collect all these numbers. We see acidity here is we get about the 9, whereas, for example, astonishingly, the melanoidins are also very fast. And then we have the caffeine that is somewhere in between, and the chlorogenic acid, depending on what we are. We have different speeds of extraction, and we get this kind of a possibility to look at the molecular level at the evolution of this compound. Now, let's go back to Brewing Chart. You can now project these compounds onto the Brewing Chart. Now what we have here is again full dissolved solids, and now we create a second axis, which is the normalized sum, we call it. For each of these compounds, for example caffeine, we can plot them in this graph by saying that here at 1 is the total amount of caffeine in the final cup. We normalize the total amount of any compounds at 1. This is the concentration of caffeine in the final cup. And then we go back and look how much is in individual fractions, and we can plot them here on this axis. In the first fraction, we have about perhaps 25% of the caffeine, then it comes up and up, and at the end it is 100%. We can plot now all these compounds into the Brewing Chart by having a second axis, which is the normalized amount. Here is the total amount of the compound in the final cup, and here are the fractions compared to the total amount. And we can now project every single compound onto the Brewing Chart, but we are introducing a second axis. And so we can see difference. So what we see, in fact, compounds that are high are extracted fast, because they come early on and then they flatten towards the end. So these two compounds are compounds that are being extracted relatively fast compared to others, and these are now the acidity and the melanoidin. This is kind of acidity. We would say that's okay. That reflects our experience. Melanoidin, we don't know why. It seems that they are being extracted quite easily. So this is a possibility to look to project our dynamic data and chemical information onto the Brewing Chart. This is a start. This is not really yet very sophisticated, but what we're trying is to keep the Brewing Chart, not making more complicated. Just by adding one single axis to bring dynamic and molecular information into it. Now the next experiment was on a mythos. Now we went back and we tried to go and compare now these results, because this work here was on a fully automatic machine. And now we went back after all this experience, and we did an experiment with a Nova Simonelli machine and a Mythos grinder, and we did all kinds of measurement. I'm going to show a few because this is work in progress. This is not yet finished. And then we measured a lot of the non-volatiles, we call melanoidin, chlorogenic acid, caffeine, and of course we measured also the aroma compound. And I'm going to show just a little bit to show you now how the Brewing Chart can be used here. The way we sampled the volatiles, I'm going to show you, I don't know if you recognize here the portafilter, and we sample it here. I'll show you more how we do that. And here are the fractions. For the non-volatiles, we collect samples, and we shift every few seconds, and we get now specific samples we can analyze individually in order to know exactly what is in each fraction chemically. Now for the volatiles, I'll just show you a little bit how that works. We have a portafilter, and here we have a small chamber. We have constructed a very small chamber where we come with air, we rinse here, and we take it out. Here is air to dilute, because the intensity is so high, we have to dilute it here with air, and also to bring the humidity down for our instrument. We cannot just go with this into the instrument that is here. So we dilute it first, the signal, at the same time, and then here we take 99% of the signal away, and only 1% goes into the instrument, because the instrument is so sensitive that we cannot just blow everything into the instrument. So, and we measure here the aroma compounds, volatiles. And the non-volatiles, as I showed you, we're measuring here. Right now I'm going to show only the non-volatile, because this is related to the brewing chart. The volatile is a totally different world, which has nothing to do with the brewing chart. It's just a separate. And so I'm going to focus now on the non-volatiles, because I'd like to make the link to the brewing chart. So first of all, the gravimetry of the Nova Simonelli, straight line, and quite good reproducibility. And so this is kind of the way you extract it on weight-wise. And then we measured, of course, again, the same samples, caffeine, melanoidin. So what we see here is that the caffeine, again, you can fit it to this. We try different models, but the same model works very fine. And you get actually very much the same dynamics on this Nova Simonelli as the fully automatic machine. So the speed of extraction from fraction to fraction is very similar, this tau. And again, the melanoidin are, again, much faster in this system. So it is a confirmation that somehow melanoidin, which is this huge molecule, come very fast. Why? We don't know that. And then the chlorogenic acid, we measured them also. We are again in the range of 13. This gives us an idea about the speed, how they are extracted from fraction to fraction. At the end, we can go back and project these compounds back onto the brewing chart. Here we have, of course, 20% in the first fraction. And here what I'm doing, this is now a plot of the individual fractions. And this is how we plot it. This is now the cup. So this is the final, like integrating the total solids over the whole cup. And whereas here, this is just the last fraction by itself and not the full cup. So here is the way you would plot the brewing chart. This is the cup. It starts the first fraction. When you measure it, this is total sort of around 20 and an extraction yield of a few. And then you continue. And what you see here compared to the fully automatic machine, where you had a little bit, it goes more like that, the change between the first and the second fraction is much bigger. You have a very high total solids in the first, and in the second you already have 5% lower, which means that in this system you extract much more relatively in the first fraction than compared to a fully automatic machine. So you see already a difference in the dynamics. And here are different compounds again. No big differences in these compounds. They are still work in progress. The melanoidin are not plotted in here. But we get here a possibility, again, to project molecular information as well as dynamic information into the brewing chart, and we can look at these. Now, finally, the third one that we are now started mostly is the filter system. We have in this case, we took a Mocha master. Again, the same idea. In the first experiment, you would like to simplify the extraction to focus on the measurements. And once we have mastered that, we can go perhaps to a manual because we create a lot of noise in a manual. Here, we have huge reproducibility, and that's the way we did it. And that's how we collect the samples. We shift it, and we collect several samples. Here are the fractions we collected. Of course, now, since it's a much longer extraction, we can select a large number of fractions. We can look more detail at individual fractions because we need a specific amount to do analysis. We cannot have like 1 milliliter fraction. It's not possible. And so we collected the fractions. And here now are the measurements of total solids. Here the total solid in the first fraction, the second, the third, and these are actually 3 repetitions. So we did experiments many, many times, and you see it's quite reproducible. That's for us as a scientist, it's relevant to show that these are reproducible data, and not just one measurement that we did. And if you plot it now as a total, as a TDS, this is TDS of individual fractions, this is the TDS as we plot it, we see that at the last fraction we end up with a TDS of 1.2. This is what we expect for a filter coffee. In the brewing chart of filter coffee, we want to have a total dissolved solid of 1.2. And if we project that now into a brewing chart, because we know what the brew ratio is and how much coffee we used, we end up for this filter coffee with this trajectory from the first fraction to the final fraction. We end up here with a TDS of 1.3 and 19% extraction yield. So we are projecting again dynamic information from a filter coffee, and now we have filter coffee, fully automatic machine, and a professional machine which we can compare. And acidity we also measure. This is of course work in progress. Now I'd like to conclude and to go back now to this summary. The effort that we're doing right now is to stick with the brewing chart, because it's something so widely used that we should find out whether we can expand the usage of the brewing chart to get now also not only endpoint information and not only total dissolved solid, but also molecular information. Can we project molecular information and dynamic information into this brewing chart and make it usable a bit more? And here is now the results from the fully automatic machine. So on one hand, we have this axis that is the one that we always use. We should maintain that. And this is the TDS. And here is now the extraction dynamics of individual compounds. We see the acidity coming earlier, melanoidin, and here are the different other compounds, which we can look into more details. What you see here is that the sharer, or this particular machine, it's actually difficult to say fully automatic machine because it's just one sharer we looked in detail. It could be that if we do a Frankie or another machine, we'll have different behavior. This is not yet shown, but this machine has a behavior from the first to the second. You have nearly the same total dissolved solid. Of course, you have also less extraction than professional, but here you have actually more fractions are relevant. There are more coming in the second and third relative to the first. When you go to the Nova Simonelli, you have a different behavior. Really, the total solid is coming very early, much more, and then dropping off in the second fraction. And you have a little bit of different evolution or a trajectory of the total dissolved solid towards the final cup that we generally look. And here are different compounds. And in the filter, Mocha filter, we have kind of also, not totally linear, but right now that's where we are, totally dissolved solid. The compounds we're working on, trying to develop the other compounds. So trying to stick with the brewing chart, but to make it a little bit more useful in aspects of dynamics and molecular. So what comes next? We're trying to, the brewing chart is very useful. Everybody uses it, most people understand it. Of course, it's quite old. It's now since the 60s. And it would require perhaps a little bit rethinking. But right now what we're doing is we're trying to include molecular and dynamic perspective into the brewing chart in order to get a little bit more information into it. But of course, the effort now also always has to go into, do we have to use a totally new brewing chart? Because grind size, temperature, many other parameters are also very important, but they just, or flavor, they are just not there in the brewing chart. And eventually there would be at some point a creative act by somebody to come up with a new way of describing extraction. The problem is it has to stay simple so that we can use it. Because we can come up with very complex models, and there's work going on. Right now we have a project where these parameters here, you can define parameters, but they are so complex to understand, which have to do with the diffusion dynamics of molecules outside the individual grains of your powder or things like that, that they will not be easy to integrate into some useful, simple tool. So this work will be going on one hand, very fundamentally to understand what are really the key parameters, and then how can we project this into a simple way of describing the extraction that can be used by people who are not physical chemists or scientists. So that's what I want to talk about, brewing and extraction, and perhaps you have some questions.
My question is, after doing all those research and trying to improve the Brewing Chart, will it mean that for baristas or people wanting to understand more dynamics during the extraction, it will require us to create new tools also to take those measurements? How do you have access to it without the tools? Because you have the tools, but yeah.
Yes, this is actually the issue, that we don't want to create something that nobody can measure. You know, today you can, for example, for water, you can measure easily by titrating. So there are simple tools that have been offered by the industry. You can measure totally dissolved solid. Yield, you calculate in general, you don't measure it. Or to measure the yield is not something we can, you know. We just, I mean, of course you can measure the weight and then dry the coffee after and measure again. Nobody measures the yield properly, you know. We measure from TDS and then we go back. You don't know how much coffee you lost in your trajectory, you know. So sometimes we did that, you know. We measure, is the yield that we are getting, is it really the yield that when we take the coffee and we dry it and we see whether it's, so there are actually some systems where you lose coffee and you have yield lost, which is not in the cup. But overall, yes, this is a challenge. And but before we go to that, we have to know which are the parameters. Right now, we're sticking with totally dissolved solid. Caffeine, I don't think anybody can measure simply. You know, it's already very difficult to measure. Acidity, people can measure. Titrable acidity is a possibility to measure. But I'm aware that everything is complex, you know, for people who don't have a lab. So the one that is closest is eventually basically you drop in some base and you measure the pH, but to measure the pH erode is not too simple for most people. It's basically impossible. It's an electrode, you have to buy that. But perhaps after a while, you know, refractometers weren't there 5 years ago. Now everybody has a refractometer. I don't know, everybody measures now roast degree, you know, which is not a cheap instrument. So these are instruments that are coming now into the regular usage of people, which are of course simple to use, but they are not simple instruments per se. So perhaps there will be other instruments coming in, simple to use, but they will have to be well selected.
All right, we've got a few.
Hiya. So pretty much I'm doing sensory. So everything you've said is kind of taking all the qualitative stuff that we've been learning and technically made it quantitative. So in the future, I'm not saying next year or the next 10 years, are baristas going to become null and void for machines?
Tell me again, yeah. I mean,
so are you going to be able to, at some point, be able to put a quantitative point, or be able to take a coffee and make it quantitative? So
about the flavor profile?
About the flavor profile and everything, and then just make our jobs.
Yeah, this is actually one of the holy grapes. You know, this is a very challenging thing, you know, to measure the flavor. And we're working on that since 10 years. And you can be successful in some small instance, but it's not easy because I don't want to go into that, but we are still far away. We can measure total we can measure total dissolved solids, which has to do with body. That works well. You can measure acidity, not too bad, with the titrable acidity. Now, when you come to measuring the aroma, there is something that we're observing now more recently is if you measure the total intensity over a coffee, that doesn't say anything about quality. And we're seeing that, for example, some of the top coffees have actually lower intensity in the volatiles, and the more even intense. So, and some of the lower Q-graded coffee, and lower I mean like 85, 82, they have more intensity than a 90. So now, perhaps, and now we're going now to trying to understand whether that could be something related to the clean cup, because a clean cup is an aspect of much, hardly anything that sticks out, you know, it's something very harmonious. So anyway, the total intensity over a cup, the total amount of aroma compound does not correlate with the Q grading quality. So I think we are still far away to predict the sensory profile.
I'd like to come back next year, so
yeah,
that'd be great.
I think we've still got jobs next year, fingers crossed. So Hannah, Davida was next.
Hello. Well, my question is about the slides and what you present before. What I understood is that not all the compounds are melt in the same time. Yeah. But the question is, it depends maybe from the molecular chain that are made. So did you find some difference between the chlorogenic acid, that really big chain of molecular, and the other compounds that maybe have different, or what?
Within the chlorogenic acid, which are similar compounds, we seem to see such a trend. So the smaller, but they are really very similar, but the smaller have a factor of 13 coming faster, and the bigger one 18. So there is a trend with the size. But then when you go to the melanoidin, which are the huge molecules, they are coming very fast. So right now, we can't say it's just a question of size. There are so many other parameters that will affect. And we don't know where these melanoidins are on the grain, because we have to get perhaps a better understanding of, perhaps in the case of chlorogenic acids, the water penetrates the whole grain and pulls it all the way out. Whereas in the melanoidin case, because they are so big, you only rinse the surface of the grains, and you will never go into it. And that's why it comes fast, and that's it. And the water will never be able to pull the melanoidin from the inside of each individual grains out. That's why you have such a fast extraction, and then that's finished. Perhaps, you know, but we don't know these things. Because it has to do now, and that's the parameter is missing, particle size distribution, grain size. These are other important parameters for the extraction.
I think you were speaking about temperature, pressure, and water, the earlier research.
Yeah.
And you were saying the water doesn't have an effect on extraction. My question is this the same for espresso as filter? And do you mean the TDS of the water or the temperature of the water? Or can you elaborate a bit?
Yeah. So scientifically, you can never say water has no effect. I do not see an effect within the resolution of my method, because I always look with some noise into everything, you know. So there's always variability in my measurements. So within the quality of my measurements, we haven't seen yet a clear sign that the water affects the extraction. So if you have water that has basically reverse osmosis water, one that has high alkalinity, high total solids, we don't see an effect on the extraction of the compounds. We see an effect on the sensory profile. So, but if we look at the compounds individually, we cannot see yet an effect. So that doesn't mean that there isn't, but we just have a precision to look at it, and we don't see an effect. And we did it now with the Nova Simonelli again. We looked into quite different waters, and again, it seems to be a trend perhaps, but there is no significant difference between waters. So right now, the way to do is to be even more reproducible in your experiment, so that if you do 3 different waters, you can eventually see, because if the differences are small, you have to have very precise measurements, very little noise on your experiment. So perhaps, but it's a small effect compared to temperature and pressure.
Hi, Chahan. Thank you for the presentation, first of all, because I know it's really difficult to explain these things in a simple way, as you are doing. I have one other question. Will you show us how the compounds are moving in dynamic way during the extraction? And as David was asking, they are related to the chemistry, physics of how the compounds are dissolved by the water. Mm-hmm. But I have the reverse question, the other side question. We could also maybe increase the efficiency of extraction or change the extraction if we modify the parameter of the machines during the extraction to change the curve or optimize or increase the efficiency of the curves.
Yes, of course we could do that. That's of course an additional complication. Pressure profile, temperature profiles, flow rate. Yeah, you're right. So these could be things to explore. Right now we are actually on a so much simpler level. If we include these parameters and we don't understand the stable conditions, then we're just adding complexity without being able to understand. So right now we're not doing any profiling. So, but of course you could, at some point, you could use these additional possibilities to influence a lot your flavor profile. People know it influences, but why? And there's not just flavor, you know, when you play around, you have 3 parameters. You have the body, the aroma, and the crema. And if you do a temperature or pressure profile, these 3 parameters will be affected eventually differently, you know. So what should be the pressure profile? And you have to think of all 3. Also the crema, the body, and the aroma are important. And they might be affected differently from a temperature profile and from a pressure profile. So it's not that simple.
Okay, we'll do one really quick question, last one, because you put your hand up as I looked at you, and then we're going to move straight on to practical.
Thank you. When you talked about acidity that you were measuring and you were able to test it by dropping in a base solution, did you test what acids are dissolving, and did you find anything that we don't already know, like citric or malic or tartaric? Were there more? Did you test that, or can you, please?
Yeah. So there are, of course, acids in the coffee we can measure. But these acids do not explain the acidity that we measure by T-triple acidity, and they do not predict the perceived acidity. So there are a lot of acids that are bound on big molecules, so acidic functions, that we do not know what they are. But they contribute to the acidity, because it's not the acidity per se that is perceived. It is the amount of acids that can react in your mouth. So it is the buffering capacity, actually. So if you measure the pH, that's the acidity. The pH is always same, and you can do an espresso or a filter coffee, you are about 5.5, 5.3, 5.6, nothing really happening, but the coffee can have very different perceived acidities. You have to measure the total amount of acids by dropping in base until it all reacts away, and then you see, okay, you had to drip 2 milliliters, 3.5 milliliters, until it came up to 6.6 pH, which is the pH of your mouth, more or less. And this resistance to come up is a measure of how much is there. What is there? We don't know. The one that we can measure does not predict the perceived acidity. Yeah.
All right, quick round of applause for Chahan. Thank you very much for the presentation.